All right, so here's the problem we worked tonight in our practicum session. We have a truss with 3 bays supported at joints A and C. So we've got a little bit of a cantilevered section here. And we need to find, using method of sections, members BC, CF, and EF. So those are those 3 members right there. And indicating those out that way gives us a good way to visualize which way we'd want to draw our section for our method of sections. So first step, we have to find our reaction forces. So let's first find the reaction forces. I'm going to go over to a separate sheet for that one. For the reaction forces, we can treat the truss as just one big block. We don't have to worry about any of the internal structure or anything like that. We've got a pinned support at A, so that'll give us RAX and RAY. And then at joint C over here somewhere, we have RCY, and only one applied force, that 10 kips. So that's just taken straight from our original drawing. We don't have to worry about all the internal structure as long as we've got some idea of the dimensions from our original drawing. So we'll do our sum of forces in the x direction. Well, there's only one force in the x direction, that's RAX. So that's equal to 0. So RAX is 0, no side loads on this structure. If we take our sum of forces in the y direction, we've got RAY plus RCY minus 10 kips equals 0. So that means that RAY plus RCY must equal 10 kips. And then we'll take our moments about joint A. So that'll knock out RAX and RAY. RCY is 10 feet away, so we have 10 RCY counterclockwise. And counterclockwise moments are positive, so we have 10 RCY. And then 15 feet away, we have that 10 kips force, so we have 15 times 10. That will cause a clockwise rotation. Clockwise rotations are negative. So solving our y direction equation, our moment equation, we've got 10 RCY equals 150. Divide both sides by 10, and RCY is 15 kips. So it's 15 kips of force, came out positive, so it's pushing up based on our drawing. We've assumed the correct direction. So let's go over and solve our y direction equation. RAY plus 15 equals 10. Subtract 15 from both sides, and RAY is a negative 5. Don't lose that negative. 5 kips negative. The negative means we assumed the wrong direction here. We assumed RAY was pushing up, but it's actually got to pull down. So RAY is 5 kips down. RCY is 15 kips up. And that's happening because everything's trying to pivot around joint C. We put 10,000 pounds over here on this cantilevered section. It's going to try to rotate the whole structure clockwise around C. It's so much force that we need to pull down with A. But because A is so far away, we don't need that same 10 kips force. We only need 5 kips. So those are our reactions. I'll go and label those out here in our original drawing. RAX is 0. RAY is 5 kips down. And RCY is 15 kips up. So now we do our method of sections. Now the method of sections, you can visualize the cutting surface you want to use by lining out the numbers that the members that you want to find, tagging those in some way, and then kind of drawing a little line through them. If you can draw a single line through all three of those members or through three members that you don't know, you can get all three of those in one solution, in one step of applying our equations of equilibrium. You do have to close the surface. We've only got the piece that cuts through the truss. We need to close it. You can either close it to the left or you can close it to the right. It has to be a closed surface. And in the practicum session, most of the students who were there closed to the right. So our surface is going to close through the right side of the truss. The reaction at C and this 10 kip force will apply to the edges of our surface. And then as we cut through, we're going to expose these three unknown forces. So let me draw the free body diagram of what we have isolated. We've isolated the right side of this truss. We're going to cut away the left side. But as we do that, we're going to replace the left side of the truss with the forces that part of the truss supplies to the right side. So we're exposing the forces at these 3 points. So let's draw the free body diagram. They're the intact members that we're keeping at joint E, D, and C. At C, we have our reaction force, which is 15 kips up. At E, we have 10 kips down. And then we have the parts that we cut. We have the truss members that we cut. That's where we are exposing the forces. And to emphasize that, I'm going to switch color here. We have replaced the force on member BC due to the piece of the truss that we've thrown away with a force that we can call FBC. We can do the same here for member CF and for member EF. So the forces in red there, those represent the force that the piece of the truss that we've isolated feels from the rest of the truss that we threw away. Now, I purposely set this problem up so that it would be pretty easy to solve. Notice here that the forces are all either horizontal or vertical. So there are no sines or cosines we have to deal with in this problem. We just have to make sure we account for all of the forces. So let's do our sum of forces in the x direction. And in the x direction, we've got a negative FBC. We've got a negative FEF. And that's it. Remember that to the right is positive, up is positive, and counterclockwise moments are positive. We can't really do anything with that equation just yet because we don't have enough information. Two unknowns. So let's do our y direction equation. For y, we've got a positive 15. We've got a positive FCF. And we've got a negative 10. That one we can solve right away. If we combine the numbers, we've got FCF. 15 minus 10 is 5, so we have plus 5 equals 0. So FCF is a negative 5. So member CF carries 5 kips of force. We assumed member CF was being pulled on by the rest of the truss. That is, the member CF was in tension. But we've gotten a negative answer. Negative answers tell us that we made the wrong assumption. Member CF must be pushed on by the rest of the truss. Member CF is in compression. So let's put our table off to the side here. We've got our loads and kips. We've got tension and compression. And we have our 3 members that we need here. We had BC, CF, and EF. So we just figured out member CF carries a load of 5 kips, and it is in compression. We assumed its intention by drawing the arrow pulling on that piece of the truss left behind, the piece of member CF left behind. Our math told us we were wrong in that assumption. So member CF is in compression. Let's do our moments. Here we have to pick a pivot point, and we only really have 3 pivot points that are going to be reasonable here, C, D, or E. If we pick E, then both forces FCF and FBC will have moments, and that's ugly. It's not terrible in this problem, but more than one unknown is never good in a moment equation. Looks like joint C is going to be the best point to pick here, because joint C will knock out the 15 kip force, it'll knock out FBC, it'll knock out FCF. The only 2 forces that will have a moment will be the 10 kip force with its line of action going down this way, and FEF with its line of action going this way. So let's start with EF. Remember, force EF's line of action is horizontal. Our pivot points here, the arm is the perpendicular distance from the pivot point to the line of action. And according to our drawing, that distance is 4 feet. So we have 4 FEF. Pinned at C, if we pull to the left at E, we're going to get a counterclockwise rotation. Counterclockwise rotations are positive. So we have a positive 4 FEF. The 10 kip force's line of action is vertical. That's 1 bay away from our pivot point, 5 feet. So we have 5 times 10, 5 feet times 10 kips. The rotation would be clockwise. Clockwise rotations are negative. So that equation we can solve reasonably quickly. We have FEF times 4 minus 50 equals 0. Add 50 to both sides. We get 4 FEF equals 50. Dividing both sides by 4. And FEF equals 12.5 kips. Comes out positive, which means our assumed direction here was correct. We assumed the rest of the truss pulls on member EF, and our math tells us our assumption was good. So member EF carries 12.5 kips of force in tension. And now that we know our value for FEF, we can go to our x direction equation. We have negative FBC minus 12.5, the value of FEF, equals 0. Now be careful with this one. There are lots of negatives floating around, so be really careful with it. I'm going to move it over to the other side here so I have a little more room to work in. We can say negative FBC minus 12.5 equals 0. We add 12.5 to both sides, we get negative FBC equals 12.5. You then have to deal with that negative 1. Maybe divide both sides by negative 1. That'll make FBC positive, but it'll make the 12.5 negative. So FBC is 12.5, but it's negative 12.5 kips. That means our assumed direction for member BC is incorrect. We assumed the rest of the truss pulls on member BC, putting it into tension. Our math tells us our assumption's wrong. So member BC must be in compression. So member BC carries a load of 12.5 kips, but in compression. So there's the problem we had in our practicum session. Practice with that and with the problems we did in lecture, and we'll do some more practice on Wednesday night.